All right, so today we want to just review compound interest, which should, again, look familiar. On your worksheet here, which is linked on the agenda, we just have this compound interest formula. Now, you can also, it doesn't always have to be interest in money in number of years, but generally it will be for us. So what we have is A of t, this is the amount we have after t years. So if you start with some initial investment and you want to know how much it's worth in 5 years, that's what we're looking for, right? So generally, you're kind of writing the formula, you're plugging a number in for t, and then you're going to find out. Later on, we'll look at, if we know how much we want to have, figure out how much we have to invest, and we'll have to use logs for that. P is the principal. I'm not sure why they call it that. It's just the initial investment. That's what the initial investment is called, the principal. It's spelled like the principal of a building, too, for a reason. R is the interest rate per year. Now, you'll need to write the interest rate per year. Be sure that's written as a decimal, right? If you put in, if it's 2% interest and you put 2, you're actually you're doing the math for 200% interest. Like, stick with that bank if you're investing. Like, that's a good thing. Like, hopefully your banker doesn't know the difference, but I bet they do. And N is the number of compounds per year. Does everybody understand what that means? Simple interest is at the end of a time period you get, to make it easy, say we get 12% interest per year. Again, that's ridiculously good interest. But if you compound once a year at the end of the year, they'd look at your investment and they'd add 12% to that. That would be a compounding of once per year. Now, say it's quarterly, right? Quarterly. That means that after the first 3 months of the year, you'd get 1/4 of the interest. So you'd get 3%, right? And then after 3 more months, you'd get 3 more percent added on. And then after 3 more months, you'd get 3% of that amount added on. Then after 3 months, you get 3% of that amount added on. So it's going to be a little bit more because the interest you got after the first 3 months collects interest for the next 3 months. Right? So it's called compounding. Usually it's monthly, though. So usually if you had a 12% compounded monthly, you're getting 1% added on every month. But you're getting interest on the interest is the idea there. So that's what we're doing there. So we have an example, and T is just the number of years that we're invested for. Mainly we're interested in later on solving for these pieces based upon some amount out here. And that's where we'll need to use logarithms. So for number 1, it says, suppose a sum is invested of $1,000 is invested at an interest rate of 12% per year. I guess I must have looked ahead here. But the amount invested was $1,000. That would be our principal. That's the initial investment. And the interest rate is 12% per year. Remember, that's 0.12. Find the amount in the account after 3 years if the interest is compounded annually, semi-annually, quarterly, monthly, daily, hourly. Ooh, that's rough, but we'll figure this out here. So with this, so if you have annually, right, that's going to be, and we're doing it for 3 years. So if it's annually, that means n would be equal to 1. And actually, you could just use simple interest calculation for this too. But if we'll go ahead and use this. So to do this one, we would get the amount after 3 years. So A of 3 would be 1,000 times 1 plus 0.12 divided by 1 raised to the 1 times 3 power. Now, again, if it's just once per year, it's simple interest. But as we look at this, we just need to type this into our calculator. So go ahead and take a minute, make sure you can type this in. Let's all make sure that we can get the correct answer before we move on. Okay, so this is our expression we talked about. I went ahead and typed that in my calculator. We have $1,404.92. If you had 93 cents, that's okay. It's fine. But it's really important to make sure that your syntax is good. Now it depends your settings on your calculator. Now mine's pretty basic and old. So the way I typed this in was I did 1,000 parenthesis 1 plus 0.12 divided by 1. I know I don't need to do that, but I'm doing it to show. And then caret 1 times 3 in a parenthesis. If you forget these parentheses, it's probably not going to work well. But what's going to be nice now is once we've typed this in, our next question is if it's compounded semi-annually. Well, guess the only thing that changes when we do semi-annually? That would be the n. Right, so we'll just go back and retype this as a 2, and we'll retype that as a 2, and we should see a different value there. Okay, so let's go ahead just to kind of write that out, and then we'll look at the rest here quickly. So in this case, n is equal to 2, so a of 3 is 1,000, 1 plus 0.12 divided by 2, to the 2 times 3 power, right? 2 is n, the number of compounds per year, and 3 is the number of years. So when we type that in here, we get, again, it's going to look just like this, right? Except there's going to be a 2 here and a 2 here. But when we do that, we get $1,418.51. Is it the same? It's a little different, right? It's a little bit more. The difference is that after 6 months you got some interest, right? And then at the end of the first year you got interest on that interest, and then each of the next 4 times as well. Okay, so take a few minutes here on this worksheet. It has you doing, you know, quarterly, monthly, daily. We'll get those down. So, of course, 4 quarters, 12 months. Usually just use 365 for daily. Hourly, 365 times 24 is what you put in for n. So go ahead and take a minute, try those. We'll come back together and see. So for example 1 here, we talked about the annually and the semi-annually. I went ahead and put the rest of the values up here. So as we look, we can see that the more times we compound per year, the more money we have. But does it seem to be reaching some limiting value? You know, it went up by, what, $14, and then $7, and then $5, and then $3, and then 8 cents. So, does that surprise you? That it has some limiting value? Is it an exponential function?
Yeah.
Will it have a horizontal asymptote? Yeah, well, not, I guess I take that back. It's because this n is changing, but as you look, this is, I guess it's, never mind, that doesn't really make a lot of sense. But it does going to have a limit, right? And we're going to be able to find a function that, because could we say every minute, every second, 10 times a second, every millisecond? Like it could just get ridiculous, right? But it is going to approach some value, and we know how to do that. That's where e is going to come out, the natural base. That's why it's a special number. The next one we had is kind of a silly problem. Okay, our second example on the worksheet is a silly example, a little bit. I mean, it kind of the Bank of Methuselah, perhaps. But suppose Fry has $93 cents in his bank account in the year 2000. If he has an annual interest rate of 2.25%, which we'll use 0.0225, how much money will be in his account in the year 3000? Year 3000 compounded accordingly. So that would be 1,000 years, right? So that's like, I don't know, invested a long time ago, right? And you lived a long time. So we'll just plug it in just like normal, correct? Again, make sure that we don't do 2.25 here and that we actually use 0.0225. And then we'll use 1,000 for the number of years, 1 for the compounding periods. And you get this number, it's about $4.2 billion. Pretty good. Now, if you now that was compounding once per year. If you think about it though, you're making like just fractions of a penny, right? Each time it compounds when it starts off. But just those extra interest on those little fractions jumps this up to $4.84 billion, right? That's like a lot of money, right? A lot. That's
I think what you're
what hundreds of $100 million. Right? Yeah, with interest or inflation. Okay, now as we look at this, from our first example, we talked about that the more you compound, the more money you get, correct? And it was even a pain doing it hourly because it was what, 87.60. It's just a lot to type in. But you could do minutes, seconds, millisecond. I mean, it could get ridiculous. So the question is, what happens to this part of the equation, right? 1 over, is that going to be R, isn't it? Oh, no, it's okay. So what we could do is, because this, and this is sort of limit arguments and infinite function, like we can't really explain this at this level, but what will happen is if you compound an infinite number of periods, right, it just keeps more and more compounds per year, right, this fraction just becomes E, right? So that was this piece here, correct? And that just becomes E, and then there's still going to be the R up here. So what this gives us is we get this formula here for continuously compounded interest, which is actually much easier to type in. It's strange that infinity is easier to work with than a finite number. But it's A of t equals P times E to the RT power. Right, so you're going to put, this is E, this is the natural base, it's about 2.81. Use it from your calculator. That's going to be your interest rate, is a decimal again, and then T is going to be the number of years you compound. Or you can also see this equation, you know, maybe it tells you that the bacteria population grows by 12% every hour, right? So then you'd use 12% for R, and you'd use T would be the number of hours. But in terms of banking, we generally use years. So for our third example here, we have find the amount after 3 years if $1,000 is invested at an annual interest rate of 12% per year, compounded continuously. This is example 1 again, correct? But we're using different, so we're continuously compounded. The principal is still 1,000. The interest rate is still 0.12. And the time is still going to be 3 years. This is what we just saw earlier. And then we're going to get A of 3 equals 1,000 E 0.12 times 3. So we have to make sure that we're able to input that into our calculator correctly. So go ahead and try that. Okay, we went ahead and evaluated this, went ahead and truncated it, and we get that the amount is $1,433.32. That's the same we saw if it was compounded hourly, correct? But it's not going to be the same number. Out the decimal pieces are going to be different, right? So this would be, but this is going to be continuously compounded. You're taking the interest rate of 12%, you're dividing it up in an infinite number of infinitely small pieces and evaluating this. Very strange kind of thing to think about. But that's why we have a new formula here. So, again, we'll see that is about the same as the hourly rate from before. And then also, we can do this in other areas as well. Okay, our last example today is a radioactive decay problem. And we're told that a radioactive substance decays in such a way that the amount of the mass remaining after T days is given by M of T equals 13E to the negative 0.015 T. So now if you think about it, if we think back to our continuously compounded interest, it was A of T equals P times E to the RT power, right? So notice there's still a T up here in the exponent. This would be your rate of decay here, actually. So you're losing, 1.5% of the substance a day. It's decaying. That's what that's saying here. And then we'll see in the first part, you might notice already, if you put T as 0 in, we're going to have 13 kilograms of whatever we're looking at here. So part A is find the mass at time T0. So that would be M of 0 is 13E negative 0.015 times 0. But we know that's just going to give us 13 times e to the 0, which is just going to be 13 kilograms. So we're all set there. For part B, how much mass remains after 45 days? I heard it was 6.62 kilograms. I had not actually worked it out yet, so I see a bunch of heads shaking out there, so I'm going to assume it's right. But the way we'd set that up would be M of 45 is going to be 13E negative 0.015 times 45. Yeah? We'll type that in our calculator. We use our E key that we talked about earlier in class. And that gives us 6.62 kilograms, right? Radioactive decay. So all you future doctors in nuclear medicine, you can calculate that stuff now.